All right, so far we've been dealing with linear motion, or translational motion means the exact same thing. So you can use linear or translational almost interchangeably when dealing with motion. And so we've dealt with things like force, acceleration, velocity, displacement, position, mass. And those are the main ones, I guess, time. And then you've got distance and speed and things like that. But let's just stick with the vectors for right now. So generally use a capital F with a vector symbol, A, V, delta X, or whatever letter you have to be using for position, M, and T. Well, this is all fine, but we know from life that not everything travels in a straight line. Some things actually spin. So let's talk about rotational motion. Or angular. Now, whether you use rotational or angular really depends upon sort of tradition. It's generally called angular acceleration and not rotational acceleration. But if you're talking to a group of physicists and you said rotational acceleration, they know what you mean. They would not pick on you for that. So they are pretty much used interchangeably. So the angular acceleration is the rotational equivalent, or analog, I should say. Analog. And the symbol used for angular acceleration, well, traditionally with the rotational stuff, physicists like to go to the Greek letters, and so alpha. Or some students refer to it as the fish. So given just a sampling of one, anyone want to venture forth what the angular analog of velocity is?
Angular velocity.
Absolutely. And the symbol traditionally for angular velocity, again, is the omega. Lowercase omega. The uppercase omega looks like a horseshoe with the luck running out. Now, I'm going to skip displacement for a second and come back to it. Position, there is a rotational analog for position. It is not angular position. It's just generally called angle. And there are a couple symbols that are traditionally used, just like with regular position. X, Y, Z, R, S are the common ones. For angle, theta, phi are probably the two most common ones. So that is a theta, and that is a phi. But sometimes alpha, beta, gamma are also used. And the rotational analog of displacement, well, the symbol is just going to be the delta, the change symbol in front of one of those. And officially, it would be called angular displacement, but traditionally, through what angle did something rotate? So displacement angular displacement. And it's just delta in front of whatever symbol you're using. Oh, these are vectors. All right, so this is just a bit of notation and some vocab there. Then we get into the other ones, like force and mass. So, a force and influence, which might cause acceleration or a push or pull. But if I'm dealing with, let's say, this notebook right here, yeah, I'm applying a force to the cover, but it's not really causing acceleration in the traditional sense. Not everything's traveling with the same regular acceleration. It is causing it to, well, basically rotate. So the rotational analog of force would be an influence that might cause angular acceleration, which is still incredibly vague, or a twist. I guess there really is nothing too formal about it. But the rotational force is called torque. The symbol for torque is the tau. There's a rotational analog of mass. It is not called rotational mass. It actually has two names. One sort of seems to be coming into favor now, but it's either called moment of inertia or rotational inertia. So we got two different names. I tend to call it moment of inertia. I think the textbook calls it rotational inertia. Other sources, take your pick which one it's going to call it. But I will use these two terms interchangeably. Just so you know, when you see moment of something, that deals with something that's rotating. The symbol, next time you get away from the Greek stuff, the symbol is a capital I. It is a scalar, just like mass is. And time, we're talking about the time something's rotating through, what would we call that? Someone be bold. Where's the boldness? I think most of you know what the time would be called.
Time.
Yes. This is time. Now, what this allows us to do is actually double the number of formulas we've worked with so far. Now there's a formal derivation you go through to get from one step to the other, but we're going to skip that. So for example, I know that displacement is equal to initial velocity times time plus 1/2 at squared. Now this is a formula that I know is in one of the videos. It's not Hewitt does. The no acceleration is 0, gives you that, and it gives you the initial velocity 0, gives you that. This is sort of the fuller equation. But the rotational analog of it is, well, just substitute in. So this is for linear or translational motion. For rotational, it's delta theta is equal to omega it plus 1/2 alpha t squared. All I did was just go to the linear over there and just write in the analog. This is a legitimate equation if angular acceleration is constant. Newton's second law. What would be the rotational analog of that?
Tau equals capital I.
Done. I'm about to ask that question, of which you will all respond in unison. Give you a moment to look it up for those who haven't quite memorized it yet. And for those who know it and are not looking it up, just inside, you can feel a little smoke. All right, here we go. What's the formula for kinetic energy?
1/2 squared.
It's not too bad considering the point we are. All right. If I have something that's rotating, what do you think the formula is going to be?
One half I omega squared.
Now, when I had you memorize that K is 1/2 mv squared, I believe one of the things I said is that you're working on your Nobel Prize winning work, the formula for kinetic energy, 1/2 mv squared. That formula doesn't change, is yet we have a different formula here. So it would seem like a contradiction. So let's see how we get from here to here. This is 1/2 mv squared, but it's built into it. But before we do that, hit a couple of background bits. What is a radian? Now, I know not everybody has dealt with radians before in here. However, I feel pretty sure some of you have dealt with radians before. What do you know about radians? How many radians in a circle? No one? You looking it up, Jennifer? What'd you get?
I'm trying to connect to the Wi-Fi right now.
Circle. Center. What do you know about circles? Come on. Tell me something you know about a circle. It doesn't have to be the motion, but it is round. Okay, I'll buy that.
Never ending.
Sorry?
Never ending.
It depends on how you look at it, but okay. Is that a circle? Why not? What's round? Is that a circle? Is that a yep or no? Like,
Yeah,
is that a yes?
yeah,
All right, so you're saying that's a circle, but you're saying that's not a circle.
no.
Suppose like then round it off this corner here. There you go, is that a circle now? Why is that a circle? Well, and that not a circle?
Distance from sense to circle.
Say it again?
Distance from center of circle.
Okay, so the distance from the center should be a constant. What is that distance called?
Radius.
All right. So I knew you knew more than the silence was indicating. So I have some radius here. Did you figure out how many radians in a circle? Anyone, now that we've warmed up and established that there's a radius here?
4.
No, not four. Not one. All right, then we'll keep going. Why are there 360 degrees in a circle?
Because it starts at one point, goes all the way back to the same point you started at.
So why 360?
Because it wouldn't be a circle if it goes 360.
Whom are we to blame for the 360? Okay, so that's 90 and 90 and 90, is that what you're going with? So, except the 90 degrees also comes from the fact that it's 360. All right, we're gonna blame the Babylonians. That's why it's 360. We're gonna connect it back to radians in a moment. Babylonians realized there are certain things that they considered to be of special significance. The number 60 was of special significance to them. Now, mathematically, even using sort of our language, 60 actually is a really nice number because it is divisible by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. It's divisible by a bunch of numbers. There are a couple numbers that are really nice. 96 is also a nice number, which is one of the reasons why Fahrenheit chose body temperature to be 96 degrees Fahrenheit. It has changed, or he was off that day. But there are certain numbers that are really special, and so Babylonians figured 60 was a special number for them. They had a base 60 system. They also recognized that an equilateral triangle was also special. It's one of the perfect shapes. Well, why not marry the two? Well, if that's equilateral triangle, all the angles are the same, so we'll make that 60, that's 60, that's 60. So far, so good. Now, if I take 6 of those triangles, so 1, hopefully drawn better than that. If you play Trivial Pursuit, it's like the pie that you're working with. If you take 6 of them, you can put them together and you get a really nice shape. So if I go all the way around, I got 60 plus 60 plus 60 plus 60 plus 60 plus 60, which is 360. That's why there's 360 degrees. And consequently, why there's 90 degrees in a right angle. Now, especially in the 19th century, there was a movement by the math people to try to get rid of all of the artificial things. I mean, why use 360 degrees? That's man-made. We want to get down to the purest form of knowledge in mathematics. So they thought, is there something that is pure about every circle? And they came to a conclusion of yes, there is. All circles have a radius, as we have established. If I take that radius, so imagine I've got a perfect circle here, despite the way I've drawn it. I take this length right here and I move it around and I sort of see how far around the circle it will go. And then I look at sort of that angle that has been created. they realized that for every circle, that angle is the exact same thing. And so they decided to call that, since this is the arc length, that's the distance along here, that arc length that creates this angle here, is equal to 1 radian. So, how many radians are there in a circle? Well, how many times can I go around a circle?
6.283.
Of course, that's not exact. What is the actual number?
2 pi.
2 pi. The circumference of a circle is 2 pi radii. 2 times the radius, so I can go around the circle with the radius 2 pi times, which is about